Our world runs on clocks, but the universe needs none. Since the beginning, it has kept perfect time through its own silent rhythms. Picture the cosmos as a grand conductor, orchestrating a symphony of time with the motions of stars and the whispers of quantum particles. Decoding these natural clocks holds the key to our greatest cosmic questions, from how stars ignite to how galaxies will end their long journeys. How can something track billions of years without a single gear or a digital display? We will travel through the expanding fabric of space, witness the steady pulse of dying stars, and even peer into the countdown of atoms themselves. By the end, you will know the hidden mechanisms that measure the age of everything. What does it feel like to listen to the universe's own heartbeat? Every galaxy is drifting further apart, as if the fabric of space itself is stretching in all directions. This steady expansion, first observed by astronomer Edwin Hubble, acts like a universal clock. By measuring how fast galaxies are receding from us, we can essentially rewind the tape of cosmic history all the way back to the beginning. The key to this is a number known as the Hubble constant, which tells us the universe's expansion rate. Think of it as the speedometer for the cosmos. By knowing how fast space is stretching now, we can calculate how long it has been stretching, giving us our estimate of the universe's age, 13.8 billion years. Modern cosmologists use incredibly precise tools to measure this constant, refining our understanding of that timeline. They do this by observing a phenomenon called redshift. When a galaxy moves away from us, its light stretches, shifting toward the red end of the spectrum. The greater the redshift, the faster the galaxy is receding, and the longer its light has been traveling through the expanding universe to reach us. Observing a supernova in a distant galaxy provides a perfect example. The brilliant flash of light from that exploding star is not just a signal of a stellar death. Its specific redshift tells us exactly how long ago that event occurred, marking a precise moment in the deep past. This makes the expanding cosmos a vast, ticking chronometer. But this raises a profound question. If the expansion rate itself changes over billions of years, does the universe's own sense of time shift along with it? To answer that, we must look beyond the motion of galaxies to the very engines that drive this cosmic clockwork. Some stars breathe, their light swelling and fading in a slow, steady rhythm. These are the variable stars, celestial lighthouses whose predictable pulses cut through the dark. Among them, the Cepheid variables serve as the universe's most reliable metronomes. Their secret lies in a perfect relationship discovered over a century ago by astronomer Henrietta Leavitt. She found that the longer a Cepheid star's pulse, the greater its true intrinsic brightness. A star that takes 40 days to complete its cycle is far more luminous than one that pulses every 5 days. This period luminosity relationship gave astronomy its first true measuring stick for the cosmos. By comparing how bright a Cepheid appears from Earth to how bright we know it truly is, we can calculate its distance with stunning accuracy. The engine of this cosmic clock is a delicate balance of pressure and gravity. Deep within a Cepheid, helium atoms are ionized, becoming opaque and trapping the star's radiation. This trapped energy pushes the star's outer layers outward in a great expansion. As the star swells, the pressure drops, allowing the helium to recombine and become transparent again. The radiation escapes, and gravity pulls the outer layers back inward, starting the cycle anew. This continuous, rhythmic breathing turns the star into a standard candle, a beacon whose known brightness allows us to mark time across immense voids. This single discovery reshaped our cosmic perspective. Edwin Hubble used Cepheids in the Andromeda Nebula to make a monumental discovery. By identifying these pulsing stars, he proved that Andromeda was not a cloud within our own Milky Way, but an entirely separate galaxy, vastly distant. This revelation flung open the doors to a much larger and older universe than anyone had previously imagined. Every time an astronomer measures the pulse of a Cepheid, they are using a rhythm set in motion by the star itself to timestamp an event millions of years in the past. It connects us across incomprehensible spans to the very fabric of deep time. Yet for all their reliability, these steady heartbeats are ultimately temporary. The same forces that create such perfect rhythms also sow the seeds for a far more violent and final kind of cosmic clock. That steady heartbeat of a star ends in a final, brilliant flash, a cosmic hourglass that turns stellar death into a precise measure of time. A supernova is one of the universe's most violent and luminous events, the explosive death of a star. But in its fading light, astronomers find one of our most reliable clocks. Among these cosmic explosions, Type 1, a supernova, are the true gold standard. They occur in a specific way when a dense white dwarf star steals material from a companion until it reaches a critical mass limit. This triggers a runaway thermonuclear explosion that is remarkably similar every single time. Because the explosion always happens at the same mass threshold, the peak brightness is incredibly consistent. It is like a standard light bulb placed at different distances. You can tell exactly how far away it is by how dim it appears. This consistency makes Type 1 a supernova perfect for measuring vast cosmic distances and, by extension, the time it took their light to reach us. Researchers working on supernova cosmology projects made a stunning discovery using these stellar explosions. By comparing the apparent brightness and redshift of distant supernova, they found that the most ancient ones were fainter than expected. This meant they were further away than the steady expansion model predicted. The only explanation was that the universe's expansion is not slowing down but accelerating, propelled by a mysterious force now called dark energy. This revelation, which earned the Nobel Prize, completely reshaped our understanding of cosmic fate. The key to this discovery lies in the supernova's light curve, the precise graph of how its brilliance rises and falls. After the initial dramatic flash, the brightness peaks and then begins a steady, predictable decline, powered by the radioactive decay of nickel-56 into cobalt-56 and then into stable iron. The brightness of the explosion halves in about 15 days, creating a reliable timeline that allows scientists to pinpoint exactly when the event occurred in the deep past. A famous example is supernova 1987A, the closest supernova observed in modern times. While not a Type 1A, its light curve was meticulously tracked and matched theoretical models almost perfectly. Its observed fading confirmed our understanding of how these explosions seed the cosmos with heavy elements. The very iron in your blood was forged in such an event. What does the incredible uniformity of these explosions tell us? It suggests that the fundamental laws of physics, the rules governing these immense energies, are the same across the entire observable universe. These stellar endpoints provide a timeline for cosmic evolution, but to measure time on an even more fundamental level, we must look to the steady, silent decay of the atoms they create. Deep within every atom lies a silent, unchangeable rhythm. Radioactive elements act as the universe's most fundamental timekeepers, tiny hourglasses that turn over with perfect predictability. The science of reading these atomic clocks is called nucleocosmochronology, a method that uses the decay of isotopes to timestamp the creation of the elements themselves. When a massive star ends its life in a supernova, it forges heavy, unstable atoms and scatters them across space. These radioactive isotopes begin their slow, steady transformation into stable daughter elements, a process that continues for billions of years. By finding the oldest stars in our Milky Way and analyzing their light, astrophysicists can measure the present-day ratio of a parent isotope, like uranium-238, to its daughter product, lead-26. With a half-life of 4.5 billion years, this uranium decay chain is a perfect chronometer for events on galactic timescales. It tells us that the oldest stars in our galaxy formed around 13 billion years ago, not long after the Big Bang. But we can also look closer to home, to the ancient building blocks of our own solar system preserved in meteorites. The decay of iodine-129 into xenon-129, with its half-life of just 15.7 million years, acts as a precise stopwatch for a specific moment in time. Because this isotope decays relatively quickly, its presence in meteorites indicates it was freshly made. The abundance we find tells a clear story that a nearby supernova must have seeded our cosmic neighborhood with these radioactive atoms just before the solar system coalesced. This allows geochemists to pin the formation of the Sun and planets to about 4.6 billion years ago. How do these microscopic decays narrate the billion-year story of our galaxy? They are the indelible signatures of stellar lives and deaths, written into the very matter that now forms our world. Yet as precise as these atomic clocks are, they measure a linear, irreversible flow of time. To find a clock that might even tick backward, we must turn to the most massive and warped regions of the cosmos.